Hello and welcome to this chemistry lecture series. In this video we're going to look at chapter 17.4, which is now going to cover reactions of alcohols. So we're going to look at the reactions that alcohols can undergo, which is a fair bit of them. There are a lot of reactions of alcohols. And then we're going to delve into the reactions of alcohols with other compounds such as carboxylic acids. So we're going to see all the reactions that involve alcohols as a reactant. So let's start. The first reaction that alcohols can undergo, which is a reaction that most organic compounds can undergo, is combustion. Combustion is simply just a reaction of an organic compound with oxygen, and it's always, in the case of alcohols, going to create carbon dioxide and water. So here we're going to have our two reactants, the alcohol, whatever that alcohol may be, and oxygen reacting with each other, meaning that they're reactants, that's why we have them underlined, to create carbon dioxide and water. So this is not going to create any type of organic reaction. It just creates the simplest forms of these compounds, which are CO2 and H2O. Because the alcohol has an oxygen in it, the balancing will be slightly different than that of the combustion of alkanes. So alcohols burn cleaner than their other organic counterparts because of that built-in oxygen that they carry. Because of that, and because the temperature at which they burn is different, because they have a different structure, they're usually used as a cleaner source of power and as a cleaner fuel for internal combustion engines. So right now we use things like fossil fuels that create things like gasoline. Well, fossil fuels are going to have a bunch of different environmental issues that we have discussed in the past. Whereas alcohols created from biomass can burn a lot cleaner. Biomass are things like sugars from plants, starches from plants like corn, and even cellulose from scrap parts of plants like leaves and stems. All of these can be processed in plants and turned into alcohols, which are then used as biofuels. Biofuels are essentially just alcohols that are created from plants that we normally just cultivate for other purposes, like food or logging. So this is a very clean alternative that can be used to things like fossil fuels, diesel, and the such. So let's keep going. So that's combustion. This is pretty straightforward. Another reaction that our alcohols can undergo is a substitution reaction by hydrogen halides. So in essence, alcohols can react with hydrogen halides, which if you remember is just any halogen with a hydrogen attached to it. So something HCl, HBr, HI. These two are going to react with each other, which is why we have them here as underlined, because they're reactants. And when they do so, a substitution reaction happens. When this substitution reaction happens, the hydroxyl group, the OH group, gets substituted by a halogen, creating a halogenoalkane. This is one of the ways that we saw we can create a halogenoalkane in early chapters. When we have an alcohol, we can grab this hydrogen halide and essentially substitute this hydroxyl group, the OH, in the alcohol for the halogen. And let me actually put the halogen in a different color, but for the halogen that is found in the hydrogen halide. So the halogen takes the place of the hydroxyl. We end up with a halogenoalkane, and then the other product becomes water. The water is made because the OH group from the alcohol picks up a hydrogen from the hydrogen halide, creating that water molecule. So, one of the unique things about this reaction is that when this reaction happens, the hydrogen halide has to be dry, meaning that we cannot have an aqueous solution of it. We cannot use hydrochloric acid, for example. We need to use hydrogen chloride gas. So for this reaction to happen, we need to make that hydrogen halide in situ. In situ is Latin, and it means in the reaction vessel, or on site is really what it means, but in the reaction vessel through an alternative reaction. Meaning that this reaction happens, but we can't just react something like, this is cyclohexanol, with HCl by adding HCl to the mixture, because HCl is not stable like that. So the cyclohexanol, let me make that smaller. The cyclohexanol needs to react with HCl that was made in situ, meaning that we need to use an alternative reaction to create it. A reaction usually involves reacting sulfuric acid with a sodium halide, something like sodium chloride, sodium bromide, sodium iodide. When we react that sodium halide with sulfuric acid, as we saw in earlier inorganic chapters, what's going to happen is that we'll create the sodium bisulfate ion, compound that we see here, and a hydrogen halide. Which hydrogen halide we create, of course, will depend on which halogen we use in the sodium halide. So this is then created, which can react with our alcohol on site. So it's a two-step reaction, essentially. We create the hydrogen halide on site by mixing sulfuric acid with sodium halide, and then that hydrogen halide reacts with the alcohol to create a halogenalkane and water. So in this example, the alcohol being cyclohexanol. And so to make something like HCl, we would simply react sodium chloride with sulfuric acid in the reaction vessel, and that will create sodium bisulfate and HCl. Once we have that HCl being made in that reaction, then that HCl will, as soon as it's made, react with the alcohol, in this case cyclohexanol, and create a hydrogen halide. So because this reaction is an equilibrium reaction, the creation of the halogenalkane is not 100%. The reaction does reverse, but it does lie towards the halogenoalkane. So this reaction is very reversible. We saw earlier how a halogenalkane can be used to create an alcohol when reacted with water. So depending on the conditions that we use, this equilibrium reaction could lie further to the right, creating the halogenalkane, or lie further to the left, creating the alcohol. We will have this reaction lie farther to the right if we use low concentrations of water. If we have water, that water would react or would act as a reactant in the backwards reaction, making this equilibrium shift to the left. But by using a dry hydrogen halide, by excluding water from the mixture and making that hydrogen halide in situ by this reaction, we can push this equilibrium further to the right and make sure we have more halogenoalkane. Now this reaction is, like I said, because it's an equilibrium reaction, is not a great way of making halogenoalkanes. But it is one of the better ways of creating bromine, iodine, and fluorine halogenoalkanes. To create chlorine-based halogenoalkanes or chloroalkanes, we have much better ways of doing that. There are actually 3 different ways of creating a chloroalkane in our curriculum. There are more in general, but there's 3 in our curriculum apart from the one we just saw. We can use substitution with SOCl2 in a reaction. So if we react our alcohol with SOCl2, both of which are going to be our reactants here. So alcohols reacting with SOCl2 will create specifically a chloroalkane. We cannot use this to create any other halogenalkane. this reaction is unique for the product to be a chloroalkane. When we react an alcohol with SOCl2, what we will get is the chloroalkane, like we just saw, a hydrogen chloride, HCl gas. So not hydrochloric acid, be very careful. The hydrogen chloride is a gas, not aqueous, meaning this is not hydrochloric acid, this is hydrogen chloride. And the other product that we will get is sulfur dioxide, SO2. Both of which are gases at room temperature. So we create out of this reaction the chloroalkane, which is a liquid at room temperature, hydrogen chloride gas, and sulfur dioxide gas. This reaction is actually very useful. It is very unique to the creation of chloroalkanes, but it's very useful because when we do this, out of our three products, one of them is a liquid, which is the product that we're usually looking for, and the other two are gases. Because they're gases, they're going to bubble out of this solution, meaning that the liquid that we get after this reaction happens is simply just our halogenoalkane, or our chloroalkane specifically. It separates itself. So this is one way to undergo a reaction where the hydroxyl group, the OH group, in an alcohol is going to be replaced with a halogen, but more specifically chlorine, create a chloroalkane, and then have the reaction just, or the product just be the chloroalkane. Because that OH gets replaced with a chlorine, the other two products bubble out of solution because they're gases, and we're just left with pure chloroalkane as a product. So it's very good because it separates itself. We can reduce the number of steps we need to take. We do not need to purify the chloroalkane product. It just purifies itself. It separates itself. Now, I did mention that this is one of 4 different ways. We saw 2 already. The reaction with hydrogen halides with HCl to create our chloroalkane. There's also the reaction with SOCl2 to create a chloroalkane. But there are 2 other reactions that will create a chloroalkane. The first, or the third, I guess, is the reaction with PCl5, and the fourth is a reaction with PCl3. We can also make a chloroalkane by reacting an alcohol. Oops, let me get my highlighter here. By reacting an alcohol with PCl5. So when an alcohol reacts with phosphorus pentachloride, PCl5, it creates, again, to no shock to anyone, a chloroalkane, but also hydrogen chloride gas and POCl3. So those are our 3 products in the reaction of an alcohol with phosphorus pentachloride, PCl5. So the HCl in this case is going to give us an observation. So we got to remember that some of these reactions do have very specific observations that we can see, and we usually show those observations as a dashed line. And the observation, anytime we make HCl, really, anytime we have HCl being created, is that we're going to get steamy white fumes. Steamy white fumes is the descriptor that we use for hydrogen chloride gas. So when this reaction happens, we get the creation of HCl gas, and that HCl gas can be seen as an observation of a steamy white fume. When the alcohol reacts with PCl5, again, we get this replacement reaction of the hydroxyl group, being replaced with a chlorine. So we have a substitution reaction. And then the PCl5 reacts with the hydroxyl that's left also to create the HCl and the POCl3. Now, the same reaction can happen not with PCl5, but with PCl3. When an alcohol reacts with PCl3, on the other hand, we still get that replacement of the hydroxyl group for chlorine, but this PCl3 does require specific conditions. Those conditions being that if we carry out the reaction with PCl3, we need to heat up our solutions. So when we react the alcohol with PCl3 instead of PCl5, whereas PCl5 just reacts without any special conditions, PCl3 will need heating as a special condition. And when that happens, that reaction actually creates, as part from the chloroalkane, it's going to create phosphorus acid. Now, phosphoric, be careful with the naming, phosphorous acid, meaning H3PO3. So it creates phosphorus acid instead of the hydrogen chloride gas that we saw earlier. So this does create an acidic condition in the reaction with that H3PO3. Now, if we're going to use anything other than chlorides here, so we can do, like I said, we can undergo this reaction with PCl3 if we heat up the condition. But we could also use the same kind of compound, but for other halogens, like bromine and iodine. We can also react alcohols with PBr3 and Pi3 in order to create other halogenoalkanes like bromoalkanes and iodoalkanes. However, if we needed to do this reaction with PBr3 and Pi3 to create other halogenoalkanes, those compounds, the PBr3 or the Pi3, need to yet again be made in situ. So whenever that reaction happens with other halogenoalkanes that are not chlorine, or to make halogenoalkanes that are not chlorine, we need to make those compounds in situ by reacting red phosphorus with either Br2 or I2, depending on which halogen we want to use here. And then we need to heat up this reaction. So let me change over to orange. We need to heat up the reaction as well. What does this do? Again, this makes the PBr3 and Pi3 in situ. So we have a two-step reaction here. We have our phosphorus reacting with our either bromine or iodine, depending on what we're trying to make. And what that does, it creates PBr3. PBr3 or Pi3 if we're using iodine are not stable on their own. And so they need to be made in situ so they can react quickly with the alcohol before they decompose. So the PBr3 is made in this initial reaction between the phosphorus and the bromine. And that PBr3 then can automatically react with the alcohol to replace the OH group for a Br, create a bromoalkane, and again create that phosphorus acid, H3PO3. So the phosphorus acid doesn't change, it still creates that. What changes is the halogen that we are using to replace the hydroxyl group. But that's only with bromine and iodine. If we are trying to do this reaction with PCl3, we do not need to make it in situ, but we do need to heat up the reaction. Whereas PCl5 does not need the reaction to be heated, and it will just react with the alcohol. This is why PCl5 and SOCl2, which we saw earlier, are usually the preferred ways of making a chloroalkane. Because they're very clean, like I mentioned earlier, the SOCl2 creates products other than the organic, which are gases, so they separate themselves. The PCl5 does not need any special conditions, so it's very easy to react, although it does make two other byproducts, which are the POCl3 and the HCl, which is steamy white fume, the hydrogen chloride gas. So that's another, there's a few ways of making halogenoalkanes, more specifically chloroalkanes, but also a few other ones, from alcohols. Now, like we saw in section 1, alcohols are also going to act like acids. And just like any other acid, because they act like acids and can lose a hydrogen, they will undergo what we call acidic conditions. So before getting to this reaction right here, I do want to take a minute and explain the difference between an acidic condition and an acid-base reaction. Or an acidic reaction, should I say, and an acid-base reaction. An acidic reaction is a reaction that can normally be carried out by an acid. It's a reaction where the hydrogen is lost from the acid, creating an H plus ion. This is different from an acid-base reaction, mainly in name. Now, in an acid-base reaction, the H is still lost by the acid, creating that H plus ion, but it reacts with a base. Or what is considered to be a base, right? So things like sodium hydroxide, ammonia, NH3, potassium hydroxide, that kind of thing. So in an acid-base reaction or a neutralization reaction, which is even more specific because neutralization reactions need to create water, the acid is reacting with a base. It's still losing its hydrogen. That's what makes it an acid. This little chunk right here is what makes it an acid. But it's reacting with a base. Whereas an acidic reaction, or a reaction where something is acting acidic or like an acid, it means that that thing is still losing the hydrogen, creating H+, which is, what makes it an acid. But a base might not be needed. The reaction that we're about to see, where an alcohol reacts with sodium, is an acidic reaction of alcohols. One where the alcohol is acting like an acid in the sense that it's losing its hydrogen, but it is not reacting with a base. It's in this case reacting with an active metal, like sodium. So let's look at that. And this is all semantics, of course. I mean, the process is all the same. You're still losing a hydrogen. But let's look at this reaction. So alcohols can react with sodium because of their acidic nature. Sodium metal, which we often call an active metal or a reactive metal because it is in group 1 and it reacts very violently with a lot of things. So sodium metal can react with alcohols where the alcohol will act as an acid. So the sodium metal will react with an alcohol in an acidic reaction, and what it's going to do, it's going to start creating bubbles. Why bubbles? Because when the hydrogen loses its, or when the alcohol loses its hydrogen, creates hydrogen ions, which then can bond together, they create hydrogen gas. So whenever the sodium metal reacts with an alcohol, we get a hydrogen gas being created because the hydrogens are lost by the alcohol, and we also get what we call an alkoxide ion. And you can view an alkoxide ion as the hydroxide of an alcohol, right? When water loses hydrogen, it becomes hydroxide. When an alcohol loses hydrogen, it becomes alkoxide. So an alcohol plus sodium will create a sodium alkoxide salt, which has the alkoxide ion with the sodium, and I'm going to show you in the bottom what it looks like in a second, and hydrogen gas. That hydrogen gas that's created is responsible for the observation in this reaction, which are bubbles. And those bubbles are of hydrogen gas. So, sodium metal plus alcohol creates hydrogen gas plus an alkoxide ion, sodium salt. So I'm trying to highlight the part here at the bottom. And then we will see hydrogen gas bubbles when this happens. So, in this reaction, what happens actually is the same thing that happens when water reacts with a sodium ion or sodium metal that we saw in the inorganic chapters. The water loses a hydrogen or loses hydrogens when it reacts with sodium, and those hydrogens create hydrogen gas. The hydrogen gas is what bubbles, and it creates sodium hydroxide. Why sodium hydroxide? The hydroxide comes from the OH from the water that has lost its hydrogen. So like I mentioned here, what is an alkoxide ion? An alkoxide ion is the alcohol version of the OH. Because when an alcohol reacts with sodium, the alcohol is going to lose its hydrogen as well. The hydrogens lost by the alcohols come together to create hydrogen gas, which is why we see bubbling. The rest of this alcohol, the O with the whole carbon chain, becomes what we call the alkoxide ion. Now, that alkoxide ion is essentially just an alcohol without its hydrogen, and because this bond broke heterolytically, and both of these electrons went to the oxygen here, this oxygen has an extra lone pair of electrons, making that oxygen have a negative charge. So this is a negative ion called an alkoxide ion. Again, the O minus is where the OH in hydroxide comes from. It has the same characteristics as a hydroxide, but instead of a hydrogen, it has a whole carbon chain. So this is an alkoxide ion. But because we use sodium as a reactant, that alkoxide ion is going to react and pair up with, in an ionic bond, to the sodium plus ion that's created. This sodium in this process loses electrons, becomes sodium plus. The sodium plus is going to see the alkoxide ion with its negative charge, and tell me like, how you doing? Creating an ionic bond. So this is a perfect example of a situation where we have both ionic and covalent bonds coexisting. The alkoxide ion created during this reaction is covalently bonded. It's essentially a whole organic molecule that has a charge on one specific atom, very similar to the carbocations that we saw earlier, but with the oxygen having a negative charge instead of a positive one. The sodium ion, which is just a normal ion as we've seen before, is charged positively, so it's going to be attracted to a negatively charged alkoxide ion, creating an ionic bond. So this compound, this what we call an alkoxide sodium salt, is going to be ionically bonded between the ions, but the alkoxide ion is going to be covalently bonded in general. So how do we name an alkoxide ion? We would just use the name of the alcohol, but instead of the OL ending, we will replace that OL ending for a oxide ending. So one propanol creates one propoxide ion. And then we put sodium in front of it because it's paired up with the sodium ion. So this will be sodium 1-propoxide. You're probably not going to be asked to name these, but you might see the names, and so it's good to be able to read and learn how to read these names and what they mean. So let's talk about the reactions that we have here. The water compared to the alcohol, and I should say that this is like misprint here. They should have a 2 here in front of the water. So when we react the water with the sodium versus an alcohol with the sodium, the reaction between sodium and the alcohol in the bottom here is going to be slower and less vigorous than the reaction of the sodium with the water. So this reaction at the top will be faster. Let me write that down here. Whereas this reaction at the bottom will be slower. And that's due to the alcohol's carbonyl chain. or the alkyl chain, should I say, not carbonyl. The alcohol's carbon chain, the alcohol chain. The longer the alkyl chain of that alcohol, the less bigger this reaction becomes. You do have to remember that the OH bond is polar, and that the alcohol, the carbon chain on the alcohol is going to be electron donating, which is going to cause this bond to become less and less polar, slowing down this reaction. So the alkyl group, the longer the carbon chain is on the alcohol, the slower that reaction becomes. So just to show you a few examples, if we had the reaction between, we'll do 4 here, sodium, 1, 2, 3, 4, and 4 different things. So we'll do reaction of sodium with water, the reaction with sodium and, let's do ethanol, the reaction between sodium and, let's do 2-pentanol, and the reaction between sodium and, let's do 1, 2, 3, 4, 5, 6. We'll put an alkyl chain there and an OH here. So the reaction between sodium and 4-methyl 2-hexanol. If we look at these 4 reactions, the longer the carbon chain, the more carbons are attached to the alcohol, to the hydroxyl group, the slower the reaction becomes. So as we move down this group, these reactions, from water with sodium to ethanol with sodium to 2-pentanol with sodium to 4-methyl 2-hexanol with sodium, we get slower reactions. So as we move down, they become slower or less vigorous. Although I would stick with the slower slower word here, because as we move down, the bigger these carbon chains become, the more they inhibit the reaction of this alcohol. So as we get slower reactions, what we see as far as observations, which is an important distinction, is that we get slower bubbling. Because the way that this is usually used is for a question in the AICE exam to ask you, what will you observe as we go from the reaction of ethanol with sodium to pentanol with sodium? Or what is the difference when you react 2-pentanol with sodium versus water with sodium? And because they're asking us what would we observe, we don't just say it's slower. We need to say that the observation gets slower. The observation for this reaction was bubbling because of the hydrogen gas gets produced. So as we go down, as this carbon chain gets longer, we say that there is slower bubbling as our observation. So going back here. So that's the reaction of alcohols with sodium, which is an acidic reaction. In this reaction, our alcohol is acting like an acid because it's losing its hydrogen, creating an alkoxide ion. And just, spoiler for the next few reactions we're going to see, anytime an alcohol acts like an acid and it loses its hydrogen, what is created is an alkoxide ion. Alkoxides are the conjugate bases for alcohols. They're what gets created when an alcohol loses its hydrogen. And then whether it's whatever cation it's paired up with will be what the salt name is. Sodium alkoxide if it's sodium. If this was potassium, we got potassium alkoxide. So let's look at the next reaction. Now the next reaction is an interesting one because unlike most of the reactions that we see in the AS chemistry curriculum. This is the reaction between two functional groups in organic chemistry. So instead of our alcohols reacting with something inorganic, like the sodium metal or like hydrogen chloride gas or any of those things, in this reaction, which we call esterification, two functional groups react with each other into organic compounds. During esterification, carboxylic acids, so that's our first functional group, carboxylic acids are going to react with alcohols. So we're reacting here, alcohols with OHs with hydroxide as hydroxyl group. With a carboxylic acid, we have the COOH group. So these are going to be our reactants. When these two reactions or these two reactants that are organic react with each other, what we create is a condensation reaction, which we call esterification. A condensation reaction is when two large molecules come together, and let me make a little mock-up here. When two large molecules come together to create a larger molecule, and a small molecule gets eliminated. So in this particular case, what we're going to get is that the carboxylic acid and the alcohol are going to react with each other. That's our large molecules. And they're going to create an ester, that's our larger molecule, and a water molecule, which is our small molecule. So essentially, the carboxylic acid and the alcohol get put together or bonded together into an ester through the removal of water. That's why we call it a condensation reaction. Esterification is this particular condensation reaction. And why do we call it esterification? Well, that one's very straightforward. Whenever we react a carboxylic acid with an alcohol, it creates an ester apart from that water as well. That ester is why this process is called esterification. Now, the reaction does require some special catalyst and conditions. The catalyst for this reaction is either sulfuric acid or phosphoric acid. So H3PO4 or H2SO4 would need to be present for this reaction to happen quickly enough. So those are our catalysts. And then the special condition that this reaction requires is reflux, meaning that this reaction needs to be heated in order to happen. So when we react the carboxylic acid with an alcohol, we create an ester and water. Let's look at how we will put this together, because you will be given molecules and you will need to put them together and figure out what our ester is. So we look at this example we have here. Butanoic acid is going to react with our alcohol ethanol. What happens here is that when butanoic acid or any carboxylic acid reacts with ethanol, the carboxylic acid will lose its OH group and the ethanol will lose its H in the alcohol. So when that happens, the H and the OH will create water. That's where the water comes from. The H and the OH get removed and become water, where then the rest of the compound, the carbonyl group along with the carbon chain on the alcohol, on the carboxylic acid, and the O along with the carbon chain on the alcohol, come joined together by the O, creating our ester. And you can see here by the colors, the black is the section of the ester. The carbonyl carbon chain is the section of the ester that comes from the alcohol, and from the carboxylic acid. And then the blue, the oxygen carbon chain, comes from the alcohol. you will need to put this together. So get used to the idea that all you're doing is removing the OH from the carboxylic acid and the H from the alcohol, and then bonding that carbonyl in carbon in the carboxylic acid to the oxygen in the alcohol to create this ester. Now remember that esters names come from the alcohol section, is what we call this, and the carbonyl section is what we call this. So this one particularly will be ethyl, and then because this is 1, 2, 3, 4, butanoate. So this ethyl butanoate. That will be the ester that gets created here. So that's esterification. It's a process of combining a carboxylic acid with an alcohol through reflux and a catalyst of either phosphoric or sulfuric acid to create an ester and water. Now, esterification does have a backwards reaction or a reverse reaction. This reaction, like we can see here by these arrows, these double-headed arrows, is going to be reversible. So what is the opposite of this condensation reaction? What is the opposite of esterification? The opposite of esterification is the hydrolysis of an ester. Hydrolysis, remember, is the breaking apart by water. So this makes sense. If esterification is a condensation reaction where an alcohol and carboxylic acid come together to become an ester and eliminate water, then in order to break, in order to break apart that ester that we just created, we need water. And therefore, this is a hydrolysis reaction, the breaking apart of a large molecule by water. Now, like any hydrolysis reaction, this reaction can happen with either the help of an acid or with the help of a base. So, hydrolysis of an ester requires that an ester, which is going to be our reactant, that an ester is going to break apart by exposure to water through either the use of an acid or a base, or an acid or an alkali. Now these do have to be aqueous as our alkalis because water is needed to be here to be hydrolyzed. And when this happens, the products that we're going to get are going to be a carboxylic acid, kind of, and we'll get into kind of in a second why, and an alcohol. Those are your products. The reaction does require reflux as a condition, so we do need to heat up this reaction as a condition. Now, why did I say kind of when I refer to the fact that carboxylic acids are a product? That's going to depend on what reactants we choose, whether it's an alkali or an acid. When we reflux an ester with an acid, specifically, it's going to create an equilibrium reaction. So again, we're not going to get fully all of the esters to break apart, but some of them. So I create an equilibrium reaction where we get that original carboxylic acid and that original alcohol part. So whenever we look at the hydrolysis of an ester, all we're going to do is we're going to find that carbonyl group with the O. We're going to cut that ester right where that oxygen is. And we're going to put an OH on the carbonyl side and an H on the oxygen side. That's going to give us, here's our OH that we added, our carboxylic acid. And then on the oxygen side, we add an H to the oxygen right here. And that's going to give us our alcohol. But this reaction is an equilibrium reaction, meaning that all of the ester does not get broken up. When we react this, when we heat up an ester with an acid, in an aqueous acid, which is where the water comes from, aqueous, that is going to create the carboxylic acid and the alcohol, but in equilibrium. If we wanted this reaction to not be in equilibrium, we would instead use our alkali. So if instead of using the acid, we use the alkali, the sodium hydroxide, the potassium hydroxide, to have this reaction happen, the reaction would go to completion. It is a full reaction. But because we have a base reacting with our ester, we will not get the carboxylic acid. The ethanol will still be made. The alcohol will still be made. But the carboxylic acid will no longer be a carboxylic acid. And that's because carboxylic acids cannot exist in basic conditions. And that's something that should make sense to you. Carboxylic acids cannot exist in basic conditions because they're acids, meaning they're going to react with bases. That carboxylic acid that gets created is going to react with the sodium hydroxide that we're using for this reaction. So instead of carboxylic acid, what we are going to create is what we call the carboxylate ion. And carboxylate ion is essentially the same as the alkoxide ion, but for carboxylic acids instead of alcohols. It is the whole carboxylic acid that we're creating. So look at this, carboxylate ion versus this carboxylic acid. It is the exact same thing, but it's going to be missing the hydrogen. And because it's missing the hydrogen, it has that negative charge. So because it's missing the hydrogen, it has a negative charge, so it's an ion, and it's called the carboxylate ion. It is just carboxylic acid minus a hydrogen. And it's going to pair up with the sodium ion that gets created from the sodium hydroxide here. So we're going to get a sodium carboxylate salt, in this case sodium butanoate, and our alcohol. So both of these hydrolysis reactions have their pros and cons. The reaction with the acid will create the carboxylic acid and the alcohol, but it's a reversible reaction, it's in equilibrium. Whereas the reaction with the alkali will not be in equilibrium, but it will create a carboxylate ion instead of the carboxylic acid, since that carboxylic acid cannot exist under acidic or the basic conditions. All right. So that's the hydrolysis of an ester. This reaction is the exact opposite to the esterification reaction that we just studied earlier. And then the next reaction we're going to look at is a dehydration of an alcohol. Now, this reaction is something that we saw the reverse of in chapter 15. The dehydration of an alcohol is the opposite of the addition of steam to an alkene. When an alcohol is heated in the presence of a catalyst, which the catalyst specifically is aluminum oxide, we can make water be eliminated from that alcohol and create an alkene. So during this reaction, an alcohol is going to be our only reactant. Let me make that bigger. Our alcohol is going to be our only reactant. But that alcohol has to be submitted to a number of conditions. It needs to be exposed to aluminum oxide as a catalyst for the reaction to happen. So aluminum oxide is going to be our catalyst. Alcohols are going to be our reactant and our only reactant. And then this reaction, in order for this reaction to happen, it needs to be heated in the presence of that catalyst. So the alcohol is going to have to undergo the specific conditions of being heated. When this happens, then the products we're going to get out of the reaction are a water molecule that gets eliminated from this alcohol and an alkene that's going to be formed in its place. So we call this a dehydration reaction because we are removing water from our compound. We're removing water from the alcohol. Now we call this a dehydration reaction, but in reality, this is a type of elimination reaction that we learned earlier in chapter 14. So this is an elimination reaction, but the molecule that's eliminated is specifically water. And that's why we can call it a dehydration reaction, which is a specific subsection or subkind of elimination reactions. Now, in some alcohols, the reaction can actually form multiple products, a major and a minor product, because it can form isomers in the reaction. So, for example, when we react, let me see, this is 1, 2, 3, 4, 5. So this is 2-pentanol. Whenever we react 2-pentanol, we heat it up with that aluminum oxide catalyst. What happens is that the hydroxide ion gets removed, or the hydroxyl group, gets removed, and it pairs up with the hydrogen, one of the hydrogens on the carbon next door, to create our water molecule. The carbons where the hydroxyl group is and the hydrogen that's removed are going to be linked together by a double bond when that happens. So what happens? When we have an alcohol such as this, where it's a secondary alcohol, and that hydroxyl group is on a carbon with 2 different carbons on each side, then that reaction, when it happens, can either create a double bond on the right side, creating our major, one of our products, and I'll go into major and minor in a second. Let me change the color of this. So we can undergo a reaction where it creates a double bond with one side of the alcohol, so here, creating one product where that double bond is with that carbon, or we can get an alternative reaction where it creates a bond on the other side of the alcohol. In this case, this side. And when that happens, it will create this product with the double bond on that side. Because in either side of this carbon, right here, where the alcohol is bonded to, there is a hydrogen. This carbon has a hydrogen, this carbon has a hydrogen. As long as that carbon has a hydrogen, it can create the double bond with the carbon the hydroxyl group is on. So that creates 2 different products. Now there is going to be a major product and a minor product in this case. The more substituted alkene is always going to be the major product. And what do we mean by that? The alkene that has carbons with less hydrogens on them is going to be the major product. So here, this alkene has 1, 2, 3 hydrogens. If we look at this alkene only has 2 hydrogens on it, on the double bond, should I say. So because of that, this is going to be our major product, because the more substituted alkene, meaning the one with the least number of hydrogens, is going to be more stable in its making than the one with more hydrogens on it. So that's why this is a major product and this is a minor product. That's not always going to be the case. So if we had an alkene, like an alcohol, should I say, like this one, where the OH is in the middle, we would actually only get one product. Why? Whether we form a double bond here or here, we would get the same compound, which is this. Because the other option, this, is the exact same molecule. This is 2-pentanol. This is 2-pentanol. So not every alcohol will create a major and a minor product, or even multiple products. We have to be very careful about how we do these products. Whenever we have that alcohol, we remove the OH, And then every double bond that we can make from that OH is a product. But we do need to make sure that they're not the same thing, like in this case. All right. And then whichever one, if you have multiple ones, if there is one that has more hydrogens on the double bond than the other one, the one with more hydrogens will be the minor product. The one with less hydrogens will be the major product. Now this is a diagram of how this reaction is carried out. We can use our ethanol or whatever alcohol we want in ceramic wool. We put it in a test tube and we heat it up with pumice rock to dry everything out. That alcohol goes through here. The pumice rock also has aluminum oxide in it, which will react or as a catalyst with that alcohol. And then what we get out is a gas of the alkene. All right. So on to the next reaction. The next reaction is going to be oxidation reactions. Now, oxidation reactions are going to be a bit complex when it comes to alcohols, because alcohols can be oxidized into many different things depending on whether they're primary, secondary, or tertiary. Before we get into the different options here, the different types of products we will get with either primary, secondary, or tertiary alcohols, let's look at the conditions and reactants that we need first and the observations. Alcohols, again, which is why we want our reactants, because this is the alcohol chapter. Alcohols can be oxidized by exposure to a strong oxidizing agent. So an alcohol can react with something like potassium dichromate or potassium permanganate, because remember, they're both oxidizing agents. Potassium dichromate or potassium permanganate that has been acidified with sulfuric acid. So this reaction essentially needs three reactants: the alcohol, the sulfuric acid, and either potassium dichromate, which is the example we're using here, or potassium permanganate. Remember, potassium permanganate being KMnO4. Oops. So we can do this reaction with either of those, potassium dichromate or potassium permanganate. And again, whether we use either or, we do need this to be acidified, usually with sulfuric acid, so it doesn't interfere. So those are going to be our reactants: sulfuric acid, the alcohol, and either potassium dichromate or potassium permanganate. These are strong oxidizing agents. Remember, anytime you see either of these two compounds, potassium permanganate or potassium dichromate, you know it's an oxidation reaction. Now, when these alcohols get oxidized, during that reaction, we are going to see a color change. And what that color change, that observation is going to be, will depend on which of the two reactants we use, dichromate or permanganate. In the case of dichromate, the dichromate ion, which is orange, is going to be reduced, because it is an oxidizing agent, so it is reduced itself, into chromium 3 plus, the chromium 3 ion. Dichromate is an orange color, whereas chromium 3 is green in color when it's in solution, meaning that this reaction will have a color change from orange to green. And actually, it doesn't make much sense for me to highlight this green, so let's do white. So it's going to be an orange to green color change. That's our observation when we use dichromate. If we were to use potassium permanganate, we will still get a color change, but that color change, I can always use with potassium permanganate, will be purple to clear. So do keep that in mind, because these will be swapped with each other very often. Now, let's talk about products. Because when we react, whether we react potassium permanganate or potassium dichromate, we're still oxidizing the alcohol. But what that alcohol gets oxidized into depends on whether the reaction or the alcohol is primary, secondary, or tertiary. And we're going to look at these in detail one by one. But in general, primary alcohols will be oxidized into an aldehyde. So remember, in organic chemistry, oxidation is the addition of oxygen or the removal of hydrogen. The alcohols, when they're primary, get oxidized into aldehydes, but the problem is that, as we see in chapter 18, aldehydes can also be oxidized. That aldehyde will be sitting in the potassium dichromate or potassium permanganate, and it can be further oxidized into a carboxylic acid. So the primary alcohol gets oxidized into an aldehyde, which then gets further oxidized into a carboxylic acid. If we instead use a secondary alcohol, the secondary alcohol does not get oxidized into an aldehyde. Secondary alcohols will be oxidized into ketones. And again, like we will see in chapter 18, ketones cannot be further oxidized. So the secondary alcohol gets just oxidized into a ketone, and no further oxidation happens, unlike primary alcohols, which get oxidized into aldehydes, and then from aldehydes to carboxylic acids. Tertiary alcohols are a lot easier. Why? Tertiary alcohols simply cannot be oxidized. Tertiary alcohols will not have a reaction with potassium dichromate or potassium permanganate because they cannot be oxidized. And so that one's a lot easier because there is no reaction there. So let's look at the two that do react. Let's look at primary and secondary alcohols in detail and what reaction happens there. When a primary alcohol is warmed with that potassium dichromate that has been acidified, or the potassium permanganate that has been acidified, what we're going to get is an oxidation of that primary alcohol into our aldehyde. So the primary alcohol gets oxidized into an aldehyde, and as you can see, essentially what happens here is that that hydrogen that is in the alcohol, in the OH, gets removed, and a double bond gets created from that oxygen to that carbon. So the hydrogen gets removed from the alcohol, double bond gets created between the oxygen and the carbon, creating our aldehyde from our primary alcohol. Now the problem is that aldehydes can also be oxidized. And because that aldehyde is still sitting in that dichromate or potassium permanganate, it's going to keep reacting. So that aldehyde is going to get further oxidized, is what we call it, into a carboxylic acid. How does that happen? Essentially, we would just be adding from that aldehyde, which has, if you remember, that aldehyde here has a hydrogen. From that aldehyde, we would then add an oxygen to this aldehyde here, creating that carboxylic acid. So we're adding oxygen. That's why this is an oxidation reaction. So we go from a primary alcohol to an aldehyde to a carboxylic acid. But what if we didn't, right? Why, if we wanted to grab this reaction and only make an aldehyde? How will we make an aldehyde but not a carboxylic acid? How will we get this reaction to stop? If we want to avoid the creation of the carboxylic acid, we need to use a process called distillation. Distillation, what it will do is that it will separate the aldehyde from the potassium dichromate or potassium permanganate, and therefore keep it from oxidizing. The process of distillation is a process of separating components or substances in a mixture by using selective boiling and condensation. We'll talk about distillation in the next slide, but essentially what distillation does is that it separates different liquids based on their boiling point. This is the same distillation that we use for things like creating vinegar, creating alcohols, spirits, that kind of thing. And we're just separating different organic compounds based on how they boil, based on the boiling point. So essentially what will happen is that the alcohol, that primary alcohol we talk about, alcohol, not primary. The primary alcohol we talk about would react with the dichromate and create an aldehyde. And before that aldehyde can be further oxidized into carboxylic acid by dichromate, we remove it through the process of distillation. We essentially boil it, we turn it into a gas, so this is a liquid, we turn it into a gas and remove it from the mixture while the reaction is happening. So let's look at how we accomplish that. This is what a distillation setup looks like. This is essentially the process of a liquid mixture being separated by one of the liquids boiling and the other one not boiling. Whenever we have a mixture of chemicals and we heat them up, if they have different boiling points, so the aldehyde has a lower boiling point than the boiling point of the alcohol, which is higher. So we react that alcohol with everything that we need to react it with. It turns into the aldehyde. So let's say, for the sake of argument, and I don't know the exact numbers here, but let's say the boiling point of the aldehyde is 30 degrees Celsius and the boiling point of the alcohol is 70 degrees Celsius. Well, what happens here is as the aldehyde gets created, if this flask is at 30 degrees Celsius, it starts to boil. It starts to turn into a gas. The key here is that when we have a mixture like this of aldehydes and alcohols or any mixture of liquids, if this is at 30 degrees Celsius and the aldehyde or whichever has a lower boiling point is boiling, it's turning into a gas, the temperature in this flask will never go over 30 degrees. The temperature in this flask will not start going over 30 degrees until all of the aldehyde is gone. It will not go above the boiling point of the mixture component that has the lower boiling point until all of it is gone. So what happens? As this mixture starts to boil, only the aldehyde is boiling. The alcohol is not boiling. It is not turning into a gas. So that aldehyde that is turning into a gas is going to evaporate, go out through this tube, which we call a condenser, and in the condenser, it's going to turn back into a liquid. So here, the liquid aldehyde turns into a gaseous aldehyde because it's boiling, but the alcohol isn't. Then the gaseous aldehyde, as it goes through a condenser, turns back into a liquid aldehyde and then gets deposited into this beaker. Why does it do that? The condenser is a piece of glass tubing that has two chambers. It has the internal tube and then it has a sleeve that does not connect to that internal tube. The sleeve we pump water in and out of, which cools down that internal tube, grabbing that gas and cooling it down into a liquid. So through this process, what we're essentially doing is that we are separating that aldehyde from the alcohol before it can react. As soon as this aldehyde being made, we evaporate it, it cannot further react into a carboxylic acid. So the process of distillation here can be used to separate that aldehyde from the reaction mixture so the carboxylic acid never gets created. So this is used for a number of other purposes as well, but this is one of the most useful uses for distillation. Now that we talked about primary alcohols and their whole very complicated process of oxidation, let's talk about the much simpler secondary alcohols and their process of oxidation. Secondary alcohols are a lot more straightforward. When a secondary alcohol gets reacted with potassium dichromate that's been acidified and we heat it up, or again, potassium permanganate could be another option here, it will create a ketone as a product. There is no further oxidation here. Secondary alcohol gets oxidized into a ketone and that is it. That ketone does not keep reacting, nothing else happens. It's just a straight up reaction. Ketones are not going to need distillation like aldehydes will. They will just stay in the solution and not be reacted. What happens during this reaction, again, because it's oxidation, is the removal of a hydrogen. The hydrogen in the OH, along with the hydrogen on this carbon, are going to be removed, and a double bond will be created between the oxygen and the carbon. So this hydrogen gets removed, along with the hydrogen that was previously bonded to this carbon right here, because this is a skeletal formula, and a double bond gets created between that oxygen and the carbon. That's where this double bond right here comes from. Hydrogen is removed, double bond created, we go from an alcohol, secondary alcohol, to a ketone. And that's it. That's a very straightforward reaction here. So you can see here how if we react a primary alcohol, like 1-propanol, with that potassium dichromate, the reaction turns green because the dichromate gets reacted from Cr2O7 minus 2, it gets reduced to Cr3 plus, which is green. So that happens both in the primary alcohol, like propan-1-O, and the secondary alcohol, like propan-2-O. However, with the tertiary alcohol, like 2-methyl-propan-2-O, the reaction stays orange because it stays Cr2O7 minus, which is orange, a yellowish orange in color. So we can see here how the primary and secondary alcohols react with the dichromate, but the tertiary alcohol does not react with the dichromate. All right, and that is something that you should remember because you will be asked about it on the AICE exam. They will give you a number of options and ask you, for example, in a multiple choice in paper 1, which of the following alcohols would not react with potassium dichromate that's been acidified and warmed. And you have to look for our tertiary alcohol, the one that is bonded to a carbon with 3 other carbons bonded to it. And that's it. That is all of the many, and very complex reactions of alcohols for this chapter, for section 17.3. I will see you all in the next video to finish out chapter 17, as we're going to talk about the last little bit about carboxylic acids.